Hello friends, today we will discuss the Hammond Postulate and how this postulate is applied to SN1 reactions. You are familiar with SN1 reactions, that is substitution, nucleophilic, unimolecular reactions. So the basic mechanism of this reaction SN1, it is a two-step mechanism, we have seen that. So this is an alkyl halide. This alkyl halide in the step 1 of the reaction, it is forming a reactive intermediate here. Okay, so it will form a carbocation intermediate here, positively charged carbon atom here, and in the next step it will be reacting with the nucleophile, that is step 2 here, and a new bond it will be formed with the nucleophile, and the leaving group goes along with the electron pair here. Okay, so this is the basic mechanism of the SN1 reaction. Correct. Now, we have seen the rate. This is actually a two-step mechanism. In the first step, the heterolytic cleavage of the CX bond and forming an intermediate, reactive intermediate carbocation here. So, the rate of the reaction, it depends upon only the concentration of the alkyl halide, and it is independent of the concentration of the nucleophile. So, whether you change the concentration of the nucleophile or you increase it or decrease it, etc., the rate of the reaction is not affected. Correct. Now, the rate of the SN1 reaction further, it increases as the number of R groups, that is the alkyl groups on the carbon atom with the leaving group increases. That is one point. And another point is the stability of the carbocation. As the stability of the carbocation increases, the stability of the carbocation, it will increase as the number of R groups on the positively charged carbon atom increases here. So we have seen that in methyl carbocation, then we have this the primary, then we have secondary, and then we have tertiary. So carbocations here. So the primary, which is more stable here, the tertiary carbocation, it is the most stable one. Also, the rate of an SN1 reaction, it increases as the number of R groups, the alkyl groups on the carbon with the leaving group increases. Then the stability of the carbocation increases as the number of R groups on the positively charged carbon increases here. Therefore, this is the order here. So tertiary, then we have secondary, then we have primary. So the reaction rate and the stability of the carbocation. So the tertiary carbocation, that is the most stable one. That is the number of R groups. That is the alkyl groups on the positively charged carbon. It increases here. That is, the rate of an SN1 reaction increases as the stability of the carbocation increases. That is our conclusion here. That is, the stability of the carbocation increases as the number of alkyl groups on the positively charged carbon atom increases. And in the same way, as the number of alkyl groups, R groups on the carbon atom with the leaving group increases, the rate of the SN1 reaction increases. Therefore, we can conclude the rate of an SN1 reaction, it increases as the stability of the carbocation increases. Okay, as the stability of the carbocation increases, the rate of the SN1 reaction increases. That is our first conclusion here. Now, what is this Hammond postulate here? The Hammond postulate, it relates to rates. The postulate relates to rate of the reaction, to stability, rate versus stability. That is our Hammond postulate. That is rate of the reaction versus stability of the carbocation. Okay, so now it deals with the energy in the transition state. So we have discussed in our earlier classes what is the transition state and all. Okay, what is the transition state actually? So let us see. Before this, I just will give a brief introduction about the transition state. That is the least stable configuration through which the static materials pass during the conversion into products. The static materials undergo the reactions and become products, convert into products, and there will be a least stable configuration in between. That is the transition state. So it is generally referred to as an activated complex or a transition state. We can call either way here. So this is merely a highly unstable state that is passed through in a dynamic process, rather we can say, and it is not a discrete molecular species. Transition state is not a discrete molecular species. It is not an intermediate that can actually be detected or even isolated here. Okay, now just briefly I will tell you, in a hypothetical reaction, for example, see, so what is this transition state? You should have a basic understanding of the transition state before we proceed further here. Okay, now what is transition state? So that, a hypothetical reaction we can just presume here. Say for example, say A, B is a hypothetical reaction. So this will be reacting with C. Okay, so this will be giving you A minus, then BC. Correct? So BC, that is a new bond form. So in this case, AB, this bond is broken here. It is partially broken. In a transition state, this AB bond is partially broken and BC bond is partially formed. Correct? That is a hypothetical reaction. Correct? The bond between A and B, it is partially broken, and the bond between B and C, it is partially formed. So A will gain a negative charge, partial negative charge, and C, again, C will lose a charge. Correct? In the course of the reaction. So each atom, it will be bearing a partial negative charge in the transition state here. So how will we represent this transition state here? It is not an intermediate. It cannot be isolated. These things all we have discussed earlier. So the transition state will be, say, A. So this bond AB partially broken, and BC bond, it is partially formed. So like this, and a double dagger, superscript double dagger we can say. So this will be a partial negative charge over here, partial negative charge here. So it's a rough representation we can say of a transition state, somewhere in between, the structure of the starting material and the product here. Correct? So the partially, the bonds partially broken and the bonds partially formed, partial charge. These are all represented using dashed lines here. Correct? Now, the Hammond Postulate, it relates rate versus stability. How the rate of the reaction is influenced by the stability in the transition state here. Okay, so it will be dealing with the energy. Organic reactions, we have seen that energy, energy is either consumed or energy is either released, and all these kind of things. So the postulate deals with energy of the transition state. This is the transition state here. So energy of the transition state. Okay, so energy of the transition state, it will determine, say, the energy of activation. So what is energy of activation? We have seen energy of activation, EA. That is the energy between the starting material and the transition state here. So energy of transition state, it will determine the energy of activation. Energy of activation is the energy needed for the starting material to cross over that energy barrier. And then only the reaction will proceed. That is the minimum amount of energy needed for the reactants to pass through the transition state and form products there. So EA, that is the energy of activation. Now, energy in the transition state, energy of transition state, it will determine the energy of activation. And therefore the reaction rate, the energy of activation is related to reaction rate. Okay, so how it is related to reaction rate? That is actually the bond breaking. Bond breaking, the activation energy high compared to the bond formation. So activation energy high means it's a slow reaction. That is a rate determining step here. Therefore, all these things are interlinked here. Okay, now the transition state determines energy of activation, and this energy of activation will determine the reaction rate. So rate and stability and all will come here now. So how will you determine the relative rates of two reactions? Now we have to see the relative energies of the two transition states there. So relative rates of two reactions. How will you see? The relative energy of the two transition states we have to see. So according to the Hammond Postulate, the transition state of a reaction, it will resemble the structure and energy, okay, of the species. That is, Hammond Postulate is the transition state of a reaction it will resemble in structure and energy of the reactants or products to which it is closer in energy. Correct? Transition state of a reaction, it will resemble, that is, it will be very close to that. That is, it means that the structure, transition state will be close to the structure and energy of the reactants and products to which it is closer in energy. So this is what the Hammond postulate states there. Now let us see an endothermic reaction. Endothermic reaction means what? That is endothermic reaction. That is a bond cleavage and all bond breaking. The energy is absorbed. Energy is absorbed here, and exothermic energy is released here. So in the case of an endothermic reaction, the transition state is closer to energy of the products. How? Let us see that. And in the case of an exothermic reaction, the transition state is closer in energy to the reactants there. So let us see the energy diagrams here. Again, we are back to energy diagrams. Unless I draw this energy diagram, you won't be able to follow endothermic, exothermic, and all these concepts here. So this is the coordinate here, the x coordinate, x axis. So we write here, this is the reaction coordinate. That is the reaction pathway, reaction coordinate. And here we will be plotting this energy level. Okay, so in the, how it will be endothermic reaction. Let us see endothermic reaction first. Endothermic reaction, the transition state, it will be closer to energy of the products here. Correct. Now, the transition state, it will resemble the products here more. The products are higher in energy. In the case of endothermic reaction, the products are higher in energy than the reactants there. Okay, because the bond breaking is involved here. So, this is will be, let us see, here is our products here. Then it will be going like this. Correct. Or slightly we can, this is our, see, this will represent an endothermic reaction here. So this is the transition state, TS, transition state here. So here you have the reactants here, and here it is the products. So in the case of an endothermic reaction, the products are higher in energy compared to the reactants here. So because the bond breaking is involved here. Okay, so in the case of endothermic, so this is the products and this is the transition state. Now we can see the energy level here, which is closer to what? So the transition state, it is closer in energy to the reactants or the products. That is what we have to see now. The transition state in the case of an endothermic reaction, it is closer to energy of the products here, because this is the energy level of the products here, and this is the energy level of the reactants here. Okay, so we can see this is the transition state here. So this transition state, see, like this, if you see, this is the energy level here. Like this we can see here. So endothermic reaction, so the energy of the transition state, it is closer to the energy of the products here in the case of an endothermic reaction now. Correct. Now, if you see an exothermic reaction means the products are lower in energy than the reactants here, resulting in release of energy. Okay, so in the case of exothermic reaction, now this I will change here instead of, so this will be exothermic. In the case of an exothermic reaction, now here this is the reactants here. The curve will be having a shape of this nature here. So this is our transition state, TS. So here it is the reactants here, and this is the product here. Okay, now here we can see the transition state, energy of the transition state here. In the case of exothermic reaction, the transition state, it is closer in energy to the reactants here. Okay, this is the energy of the reactants here, and this is the energy of the transition state here. So this is closer in energy to the reactants compared to that of the products here. This is the products here, energy of the products here. Correct. So the transition state, it resembles the reactants more. Hammond's postulate here. Okay. Now because the products are lower in energy here compared to the reactants in the case of an exothermic reaction here. Correct. So next point here, how will you conclude this one? That is, the conclusion is, in the case of endothermic reaction, the transition state resembles the products. Endothermic reaction, endothermic transition state, it resembles products. Okay, so in the case of exothermic reaction, the transition state resembles the reactants. Correct. So this is our conclusion here. So what happens then? Suppose we are, the reaction rate, rate of the reaction. If the energy of the product is lowered, what will happen to that? Because now we are seeing the transition state in an endothermic reaction, it resembles the energy of the products, and the transition state in exothermic reaction resembles that of the reactants. So what will happen if, to the reaction rate when the energy of the product is lowered? When the energy of the product is lowered means the product are becoming more and more stable. The stability of the product, we are concerned with that. So now let us see an endothermic reaction here. Okay, so when an endothermic reaction, what will happen to the rate of the reaction when the energy of the product is lowered here? Now, in the case of an endothermic reaction, we have seen the transition state resembles the more of the products here. Transition state in an endothermic reaction resembles the product here. That is the energy and structure and whatnot. Okay, so the transition state resembles the product. So anything that stabilizes the product, anything that since it resembles, transition state resembles the product, anything that stabilizes the product, that means anything that lowers the energy of the product, it will stabilize the transition state there. Therefore, lowering the energy of the transition state, it will decrease the energy of activation. Correct. If we lower the energy of the transition state means the activation energy will be lowered. Why? Because activation energy is nothing but the difference in energy between the starting material and the transition state here. Now, anything that stabilizes the transition state, that means the energy of the transition state will be lowered. Once the energy of the transition state is lowered means the energy of activation, EA, that is also lowered. Energy of activation is lowered. So, when the energy of activation is lowered, the reaction rate increases. Okay, how these are all interlinked. Now, let us explain it once again. So, endothermic reaction, the transition state resembles the products. So, anything that will stabilize the product, okay, anything that stabilizes the product, that means anything that decreases the energy level of the product, it will stabilize the transition state. Okay, it will stabilize the transition state means the energy of the transition state, it will be lowered. And once the energy of the transition state is lowered means the activation energy will be lowered. Correct. Therefore, the rate of reaction, it will increase. Okay. Now, suppose there are two, possible products. of an endothermic reaction. Again, we will be discussing an endothermic reaction. There are two possible products of an endothermic reaction. So one is more stable than the other. Okay, two products are possible. One is more stable than the other products. That is, more stable means the energy level, it is low, lower energy. According to the Hammond postulate, the transition state to form the more stable product, it is lower in energy. So this reaction should occur faster. The rate of the reaction, we are concerned with the rate of the reaction here. That is, two possible products in an endothermic reaction. One is more stable compared to the other one. More stable means it will be more, lower in energy. Correct. Now, according to this Hammond postulate, the transition state to form the more stable product, it is lower in energy. So this reaction, it should occur faster. That is, the rate of that reaction, more stable product, okay, that will be more. Therefore, in an endothermic reaction, we can conclude the more stable product, the stability of the product, okay, the more stable product, it forms faster. The rate of reaction in which the more stable product is formed, that will be higher. That rate will be higher. Okay. Now, this is all about endothermic reactions now. What about the exothermic reactions now? That will be very interesting here. Now, endothermic reaction, we can show it like this here. Two products are formed. How will you show this? You see, one I have drawn in a red line. So another reaction, we can show more stable product and less stable product and all this kind of a thing. This is an exothermic reaction. I will change this. Okay, now let us see. So this is the reactants in the case of an endothermic reaction here. This is, you see, one product is formed here and another will be like this. Two types of reactions. See, now which is the lower energy transition state? Lower energy transition state leads to the lower energy product here. So this reaction, which one will be? This is the lower energy transition state here. Now this is the product here. This is the product. Then this is the reactants here. Okay. Now, here, this is the transition state for this TS, and this is another transition state here. Two transition states are there. Correct. So, lower energy transition state, it leads to the lower energy product here. Okay. So, this green line here, this will be a fast reaction. This will be faster because it is a lower energy transition state here. This is the fast reaction and this one will be a slow reaction. This is our Hammond's postulate here. Okay, the lower energy transition state means it will lead to lower energy product. Lower energy product means more stable product. Correct. Therefore, that reaction will be faster here. Now, this is all regarding endothermic reactions here. Okay, now what will happen to the rate of a reaction in an exothermic reaction then? Okay, the rate of reaction in exothermic reactions. What will be the position if the energy of the product is lowered? That is, the product is more stable. Now, we have seen the transition state in the case of an exothermic reaction. It resembles to the reactants. Okay, therefore, the lowering the energy of the products means what? It has little or no effect at all on the transition state here, energy of the transition state. In the case of an exothermic reaction, that is the transition state, it resembles more to the reactants rather than to the products there. Therefore, if we lower the energy of the products, in the case of an exothermic reaction, it has no effect on the energy of the transition state here. Therefore, the energy of activation, it is unaffected because there is no lowering of the energy of the transition state here. Therefore, EA is unaffected. Lowering the energy of the product, it has no effect on the energy on the transition state in the case of an exothermic reaction. Therefore, energy of activation is unaffected. Once the energy of activation is unaffected means the reaction rate is unaffected. There is no change in the reaction rate here. If the energy of the product is lowered, whether the product is stable, less stable, more stable, etc., energy high, energy low, it doesn't have any impact on the rate of the reaction here. So in an exothermic reaction, we can say the more stable product may or may not, we can't say like that, may or may not form faster because energy of activation is similar for both products. Okay, energy of activation is similar for both products. So how will you represent that thing on a diagrammatically here? This is actually, I've changed these curves here. In the case of an exothermic reaction, so reactants and all, it will remain same here. Reactants. So the curve will be more or less, same kind of a thing. There is no hardly any change here in the rate of the reaction and all, because even if the product energy is lowered. More or less it will go like this. So from here, we can say it can come down like this. We can draw this, this is the products here, P. Okay, this is the transition state here. So energy of activation, it more or less remains the same thing here. See, this is our energy of activation, EA. Okay, so exothermic reaction, EA is more or less similar to both the pathways, both mechanisms here. Therefore, decreasing the energy of the product, it has got little effect or hardly any effect on the energy of the transition state here. Now, these energy diagrams, you have seen the importance of these energy diagrams, it will show how these energies of the transition state and the transition products, they are all related here. So, now in the case of SN1 reaction, the Hammond postulate, how it will look like. SN1 reaction, we have seen the rate determining step, it is the formation of the carbocation. That is a heterolytic cleavage of the CX bond, and it is forming an intermediate, reactive intermediate carbocation. It will be formed. It's an endothermic reaction because energy is needed for breaking the bonds here. So according to the Hammond postulate, the stability of the carbocation, it determines the rate of its formation, rate of the reaction. Okay, so rate of the reaction depends upon the stability of the carbocation. That is what Hammond postulate says here. So let us see an example how all these things are related. Let us have a look at this. So let us consider two alkyl halides. Say one secondary alkyl halide, and we can have a tertiary alkyl halide. Okay, now heterolytic cleavage. So how this reaction will be? So alkyl halide, one will be a secondary one and another one will be a tertiary one. Okay, there will be a heterolytic cleavage of a CCl bond. So which compound we should consider now? Let us see a primary, a secondary and a tertiary. So in the case of a compound of this nature, say CH3 twice CH, say Cl. Okay, so this will give a less stable secondary carbocation. CCl bond cleavage, it will be giving you a CH3 twice CH. Okay, this is a less stable secondary carbocation, heterolytic cleavage of the CCl bond. Now, if you have another alkyl halide here, if you consider this one, this will be giving you What is the type of carbocation being formed here? Ca3 thrice C plus. So this is a tertiary carbocation here. Two types. So the first step will be a slow reaction. That is a rate determining step. And the second step will be a faster reaction. Okay. So let us see the slower reaction. What is the slow step? The slow step of the reaction, it will be, so this one, say CH3, C, then this is the secondary one. So this will be giving you a secondary carbocation which is less stable. This is a secondary carbocation. It's a less stable one compared to the tertiary one. So now the reaction is slow here. Now in the second one, reaction will be faster because the stability, it depends upon the stability of the carbocation being formed there. We have seen that now. So this is our alkyl halide. So this will be giving you a carbocation of this nature. Okay, this is a more stable carbocation here. Now, Hammond Postulate, what does it say? It states reaction 2, that is the faster reaction. It is, the faster reaction, that is with the, where the tertiary carbocation is formed there, it is faster than reaction 1 because the transition state again. Correct. So, we are considering two different types of alkyl halides here, which is forming two different types of carbocation, a secondary one and a tertiary one here. That is in the case of the first reaction, that is a secondary alkyl halide giving a secondary carbocation, that is a less stable carbocation compared to the tertiary one. The second reaction is a faster reaction because it's a tertiary carbocation is involved. This is a tertiary one. Correct? More alkyl substitution, the stability increases. So Hammond postulate is that reaction 2 is faster compared to reaction 1 because the transition state to form the more stable tertiary carbocation, it is lower in energy. Okay, so that is the reaction is faster. That is the rate of the reaction. We are concerned with the rate of the reaction and the stability. That is what the Hammond postulate says there. Okay, here in this case, this is the first reaction, slow reaction 1, and this is the fast reaction. These are 2. Reaction 2 is faster because, compared to reaction 1, because of the transition state here. Again, to form the more stable tertiary carbocation, it is lower in energy. Now, how will you draw this energy diagram for this reaction? That will be very interesting. These two reactions, let us represent it on an energy diagram. Then it will be more clear, the stability of the carbocation and all these kind of things here. So let us see this coordinate we will draw. Okay, so here now this is our energy coordinate here, and this will be reaction coordinate or reaction pathway, whatever you want to call it, you can do that, reaction coordinate. Okay, energy diagram for the different SN1 reactions here. That is two different types of different SN1 reactions where two different types of carbocations are formed. Okay, now the first reaction, that is where the less stable carbocation it is formed there. So let us see what will be the nature of the, here it is a reactance here. So this curve will be something like this, we can say. Okay, so here this is our here we have this reactants here, say C, whatever it is, the Cl we can write here. This is our reactants here. So here the product, it will be, this is a secondary carbocation here. This is a less stable carbocation, less stable. Therefore, the transition state 1, TS1 here, this is the transition state 1. We can say it is a less stable transition state. Okay, that is the secondary carbocation CH3 twice CH plus, it is a less stable than tertiary carbocation. The energy, now let us see the energy of activation here, how it will be. See, now we can see the, for the tertiary carbocation, something like this we can draw. So what is the, this will be the next curve here. So this is the transition state 2, TS2 here. Okay, so this reaction, it will be a faster reaction here, because the product formed here, it will be Ca3 thrice C plus. This is a more stable carbocation. Okay, so compared to Ca3 twice here, that is secondary carbocation, this tertiary carbocation, it is a more stable one. Now, the energy of activation, if you see here, this is the energy of activation for this reaction here. Okay, this is EA2, we can say EA2, and for this reaction it will be EA1. This will be EA1, energy of activation 1. Now, reaction 1 is a slower reaction we have seen. Okay, therefore, EA1, it is greater than EA2 because of the energy consideration. EA1, that is energy of activation for reaction 1, it is higher compared to the energy of activation for reaction 2 here, where the more stable carbocation is involved here. Okay, that is EA2 is lower compared to EA1, energy of activation for reaction 1. Okay, so reaction 2 is faster than reaction 1 because the transition state to forming the more stable tertiary carbocation, it is lower in energy here. This is our Hammond's postulate here. Okay, now in the case of the Hammond postulate can be used to predict the relative rates of two reactions. That is more important thing. Relative rates of two reactions can be predicted. So this will be, it will be a faster reaction here. This is a faster reaction. Okay, now other one, it will be a slower reaction. Slower reaction. So Hammond's postulate, it can be used to predict the relative rates of two reactions. The most important point here. Okay, so this TS2, which is more stable, TS1 is less stable. That is the transition state 1, TS1 less stable compared to the transition state 2, TS2. It is a more stable transition state here. Okay, that is transition state 1 is less stable compared to transition state 2. That is a more stable one. Now, EA1 and EA2, energy of activation EA1 is higher compared to EA2. Therefore, the reaction number 1, TS1, where TS1 is there, that is a slower reaction compared to reaction number 2. That is a faster reaction. Therefore, Hammond's postulate, now we can use it for predicting the relative rates of two reactions there. Two reactions. Okay. Now, if you want to generalize this one, How we can do that? So I will just change this thing and draw another diagram over here. It's a more or less same kind of a thing. So here it is this thing only, starting material only. Now we can say the same way. See, I will draw the full diagrams here. There are two curves here, two types of reactions again here. So in this figure, the starting material say A. We can say this is A here. So this A, it will go, I mean it will give the product B here. A, it is giving B. B product we can't say, it is a reactive intermediate here. And this is our TS1, transition state 1 here. That is static material A. In the red curve, we can say A, it is passing through the transition state TS1 and it is giving a product B. That is reactive intermediate, which in this case is a reactive intermediate here. Okay, so this reactive intermediate further proceeds to by a transition state TS2 and it is finally giving a product C here. Correct. In the same way, this A, it is giving a TS3, transition state 3, then another D here, we can say, then a TS4, transition state 4, and product E. Correct. So, like this, if we can see here, that is the relative stability of the transition states. That is what we are discussing here. And the corresponding, say, the secondary and tertiary carbocations we have seen the same way. We can just generalize it and we can have a discussion. So, the static material here, it is A. It is giving a product, say B. The B in this case is a reactive intermediate. That is a carbocation. We have seen that. So the reactive intermediate B goes through transition state TS2 to become product C ultimately. So in the first part of the reaction, TS1, that is the transition state 1, it is closer in energy to B. Okay, it is closer in energy to B. In the first part of the reaction, TS1 is closer to B. TS1, that is transition state 1, it is closer to B. Correct? In energy to B than it is to A. There is a lot of difference here. Okay, and therefore TS1, that is the transition state, it will be resembling, or rather it will be looking like B more than it resembles A. A is the starting material, B is the reactive intermediate here. The energy level, if you see, that is TS2. Okay, first part of the reaction, the TS1, it is closer in energy to B, correct, than it is to A, and therefore TS1 resembles, or TS1 looks like B more than it resembles A, the static material. Got the point? Okay, now the transition is TS2, if you see. Now TS2, it is closer in energy to B again. TS2 is closer in energy to B. If you see the graph, we can just make out, the transition, TS2 is closer in energy to B than C, than the product here. There is a lot of difference in the energy level here. Okay, therefore TS2 looks more like B rather than C. Since TS1 and TS2, transition state 1 and transition state 2, are similar in structure to B, the factors that stabilize B also stabilizes transition state 1 and transition state 2. Correct? That is, again we will just explain, that is the static material A, it goes to give the product B here. The B is an intermediate, reactive intermediate. Correct. Just like our carbocation intermediate here. Now the reactive intermediate B, it goes through transition state TS2, second stage, second part of the reaction there, to become, and then the product C, we are getting it here. Okay. So we will be getting the product C here. The first part of the reaction only we can see here. Okay, the red line, we are just talking about the red line curve. TS1 here, in the first part of the reaction, the TS1, it is closer in energy to B than it is to A. And therefore TS1, it resembles or looks more like B rather than A. Okay. Now, transition state TS2, if you say it is closer in energy to B rather than C, TS2 looks more like B than C. Simple thing. Now, since TS1 and TS2, transition state 1 and transition state 2, are similar in structure to B, now any factor that stabilizes B also will stabilize transition state 1 and 2. Okay, it will be interesting here. Now, it is the same thing in the case of a secondary and tertiary carbocation. We have seen the order of stability of the carbocations there. That is, the tertiary carbocation is more stable compared to a secondary carbocation. So the transition state, in the order of stability of the carbocation, we have seen the transition state, it is similar in structure to its corresponding carbocation. Then the stability of the transition state TS3 in the other reaction here, TS3. Okay, stability of the transition state TS3 going to tertiary carbocation, it is greater than TS1 going to the secondary carbocation. So here we can say it is secondary carbocation, and 3 is tertiary carbocation here. That is the thing here. So reaction kinetics also, as per the reaction kinetics, kinetics of the reaction, that the reaction will proceed via the lowest energy pathway. The reaction will prefer the pathway that goes over the lowest energy hill, we can say. If a reaction has the choice of 2 pathways to form a secondary carbocation or a tertiary carbocation, then the tertiary carbocation pathway will be the preferred one because it has the lowest energy barrier. So this is all about our Hammond postulate. So thank you very much for listening.